Okay, so this is a short video on a simple correlation between group theory and number theory. The actual thing which I want to discuss is a proof of a very famous number theoretic theorem proposed by Euler using concepts of group theory. Okay, so this is often called the Euler's generalization of Fermat's little theorem. Okay. Fermat's little theorem. So what does this theorem basically say? The theorem basically says that if n is greater than or equals to 1 and the GCD of a and n is 1, that is a and n are co-prime, then a to the power phi n is congruent to 1 modulo n. And obviously know what phi n is, so phi n, it basically counts the number of co-prime naturals less than n. Okay, the Fermat's little theorem is what actually says is that, one sec, yeah. So the Fermat's little theorem is a specific part of this where n is a prime. So if I choose n to be a prime and a to be something which is not divisible by p, the prime p, then surely they are co-prime. Moreover, a to the power p minus 1 is congruent to 1 modulo p. That's what the Fermat's little theorem says. Okay. So what I'm trying to explain is a simple proof of the Euler's generalization using group theory. Okay. So how do we prove it? Proof. What we do is basically there is a very fine group which is called the group of units. Okay, what is basically the group of units? If you have seen my lectures on group theory, you will find that there is a group which I have denoted as UN, which considers elements k from Zn star. Zn star indicates the additive group Zn excluding the number 0, such that k is co-prime to n. Okay, and UN forms a multiplicative group. UN forms a multiplicative group. Okay. Now, what should be the order of UN? It should be surely phi of n, because by definition it contains the number of elements in UN should be the ones which are co-prime to n and less than n. So it's surely phi of n. So that's one fact. Moreover, it forms a group. That's the main point, that UN forms a group. So if UN forms a group and I choose out any element from UN, let us choose A to be an element from UN. Then what are the things which we already have in hand? Then firstly, A and N are co-prime. Secondly, we know that in case of a group of finite order, if I choose out any element out from the group, then A raised to the power of the order of the group must be identity. So let me just write it here, that if G is a finite group, if G is a finite group and small g is some element of capital G, then G raised to the power the order of capital G is identity, possibly a multiplicative group. So we can apply this here to say that A to the power the order of un is congruent to 1 modulo n. Why am I using congruent to 1 modulo n? Because this multiplicative group actually indicates that this multiplication is under modulo n. Multiplication modulo n. Okay, multiplication modulo n. So hence a to the power the order of u of n is congruent to 1 modulo n. But what is the order of u of n? So order of u of n is a to the power 5. This is congruent to 1 modulo n, and that's exactly our Euler's generalization of Fermat's little theorem. Okay. Yeah, so I guess this indeed works. If there's some mistake in this lecture, I surely want you guys to rectify me out. So what the only things which we have used here specifically, which might not be known to some of the listeners, is the term or group. And under a group, the concepts of operations like multiplication modulo n, the term of being a multiplicative group, or indeed the group of units, the structure. But this structure is sort of pretty easily defined. And once you know the concept of a group, why do we necessarily need un to be the collection of elements which are co-prime to n? These sort of concepts I have covered under my playlist, which contains important topics on group theory. You can surely go and visit that. Okay. Not doing further ado, let's end this lecture here. I hope you liked it out.